is an example. Uh, we have Christine here, runs forward with her sled at 2 meters per second. She hops on the sled at the top of a 5 meter high, very slippery slope. What is her speed at the bottom? So, first, notice they say very slippery slope, meaning ignore friction. And if you remember last time, we talked about the work done by friction and how it depends on the path. It depends on on how long the path is and the direction of your motion. So there is no friction, so we have eliminated that part. So the only interaction here, we have Christine and her sled interacting with the earth, and they are on a hill, on a slope. So let's draw something and then see what happens. So here is the drawing. So Christine starts here, and then slides, and then gets to the bottom here. I don't know what her speed is at the bottom, but I do know that her speed here, V1, is 2 meters per second. And I know that initially her height is at 5 meters, 5 meters here. I'm going to draw my axes. I'm going to call this Y, the y-axis. It looks like that. So I know that y1 is 5, and y2 here at the bottom is equal to 0. Notice if I ask you to use, if you were to do it using Newton's laws, notice that when the sled is here, versus here, gravity here points this way. It has a component that way. It's mg sine theta. Here it points this way. Here it points this way, and so on. And so the problem is you will not be able to use Newton's laws unless you know the shape here, the shape of the curve, and you know the angle at every single point. And then you have to do a very complicated integral to find out what the speed is at the end, assuming you know the shape. And then if the shape changes, then you have to do the thing all over. However, you will say, look, I have no non-conservative forces involved, such as friction. I only have gravity, the sled interacting with the earth, and then with the hill. So my system will be the sled plus earth. So sled plus earth. So what's the only external force? It will be the normal force. So let's write it down. The only outside force is the normal force. And that normal force, think about it, does the normal force do any work? Here's the thing. The normal force, unlike gravity, the normal force always points perpendicular to the direction of motion. Now, the direction of motion is this way, and the normal force is this way, so how much work is done by the normal force? Remember, work is force displacement times the angle between them. But the normal force always makes 90-degree angle with the displacement, so the work done by the normal force will equal to 0. So the normal force can be completely ignored. It doesn't matter, because the work done by it is 0. So we say, all right, we only have we only have conservative forces involved, and so the total mechanical energy at the end will equal to the total mechanical energy at the beginning. I will start from the very first step. The mechanical energy, by definition, is the kinetic energy plus the potential energy. So it's the kinetic energy at the end plus the potential energy at the end, and that has to equal to the kinetic energy at the end plus the potential energy at the end. And remember, where does the potential energy come from? It comes from the interaction of the sled plus Christine and Earth. Now, the kinetic energy, I'm interested in the sled here. is 1/2 m, whatever the mass is, and then V2 squared, plus the potential energy is the mass times gravity times the height at the end. And then, oh, what did I do? 2, it should say 1. Okay? And then the same thing, kinetic energy at the end is at the beginning is 1/2 mv1 squared plus 1/2 m, not 1/2. The potential energy at the beginning is the mass times gravity times the height at the beginning. The mass does not matter. It's gone. I want V2. So I would multiply both sides by 2. I would multiply both sides by 2. So that gives me V2 squared, because I multiplied by 2. This is gone. And I'm going to move this to the other side. When you multiply by 2 here, you just get V1 squared plus. And when you move this to the other side, you factor the g and you just have y1 minus y2. And then you multiply both sides by 2, so there is a 2 here. And so you get V2 will equal to the square root of this. So you have V1 squared plus 2g y1 minus y2. Exciting. Well, we have to plug in the numbers. V1 is 2 meters per second, so 2 squared, plus 2g, so 2 times 9.8, and then times, of course there is this square root here. Y1 minus y2, so that's 5. Y1 was 5, and y2 is 0. And we will get the number here. Let's get my calculator. So I have 2 squared is 4 plus 2 times 9.8 times 5. Take the square root. Oh, nice numbers, about 10 meters per second. Okay, so the sled will be moving at 10 meters per second at the bottom. At the top, you have kinetic energy plus potential energy. At the bottom, you have 0 potential energy, but a larger amount of kinetic energy. So think of it as you drop, you lose potential energy because you're losing height, but you're gaining kinetic energy. So if you lose something, you have to gain on the other if the energy is conserved, assuming there are no non-conservative forces. When I say energy here, I'm specifically talking about mechanical energy. All right. Now it is worth noting that, let me write it down. Here's the total energy, not just mechanical, meaning if I include the kinetic energy at the beginning, plus the potential energy at the beginning, plus the thermal energy, meaning heat, at the beginning. That's always conserved. If you include thermal energy, so you have kinetic energy at the end, plus the potential energy at the end, plus the thermal energy at the end, they're always equal. You cannot make this unequal. You can't. And this change here in thermal energy is due to those non-conservative forces. If the non-conservative forces, let me just generically say there is no friction. Just friction is just an umbrella for all the non-conservative forces. If there is no friction, then this part here, there is no change. The thermal at the beginning, thermal at the end will just be 0. I'm sorry, will cancel because there is no change. Then we will even have a stronger requirement that the kinetic energy at the beginning plus the potential energy at the beginning will equal to the kinetic energy at the end plus the potential energy at the end. All right? And this is called the mechanical energy at the beginning, and this is the mechanical energy at the end, right? So the mechanical energy at the end minus the mechanical energy at the beginning, if there is no friction, will equal to 0. If there is friction, then the mechanical energy at the beginning, this is no thermal, no friction. If there is friction, then the mechanical energy will not be 0. It will not be 0, right? It will equal to the work done by those non-conservative forces that you have involved. So if you have them, then you have to account for them. Let's do an example in that, all right? So here is a problem that I wrote that involves friction. It comes from the book. So suppose you have a mass. I will draw a picture in a moment. Suppose you have a mass, I put there 55 kilograms. It slides along a 6-meter long incline that makes a 15-degree angle with the ground. The coefficient of friction between this sliding mass and the incline is 0.025. It says here, what should the speed be? What should the initial speed of the mass be so that the speed at the top of the ramp is 2.5 meters per second? As you imagine, as the mass slides up the incline, it slows down. It slows down because it's gaining height, and so it's gaining potential energy, gravitational potential energy, and it also slows down because it's losing energy due to the friction. So at the bottom, it should have a higher speed than 2.5. So let's draw a picture here and remember that we have friction in this case. So here is the picture I would like to draw. You have this. The mass is here at the beginning. Let's call that speed V1. We do not know what V1 is, so I'll put a question mark here. And let's say here's my, this is the height here. This is y1 is equal to 0, and then y2, we will figure it out in a moment. This is 15 degrees, and the ramp is how many meters long? 6 meters. Yeah, the ramp is 6 meters. From here to here is 6 meters. So what should this height be? So this divided by this is the sine of 15. So this height will be, the height will be 6 meters times the sine of 15. So it will be 6 meters times the sine of 15 degrees. We will figure it out in a moment. Sounds good. And then we would like, when the mass gets to the top here, we would like V2 to equal to how much we want it to be? 2.5 meters per second. Okay. So I will use conservation of energy, but I have to remember that I have an additional force that's doing work, which is the force of friction. So I would say that the energy at the end minus the mechanical energy at the beginning will equal to the work done by the friction, the work done by this non-conservative force, the work done by friction, by the force of kinetic friction. The energy at the end is is the kinetic at the end plus the potential at the end. So it's 1/2 mv2 squared plus mgy2, mass times gravity times the height at the end, minus the kinetic plus potential at the end. So minus and minus again. So minus 1/2 mv1 squared at the beginning, I should say, and then minus mgy1. Okay, so that's this part here is the is the energy at the end, and then minus the energy at the beginning. And that should equal to the work done by friction. Okay. The work done by friction would be force times distance times the cosine of the angle between them. It would be the force of friction, force of kinetic friction, so force of kinetic friction, times the distance moved. So here is the object. As the object rolls, here's the object. Let's just take a point here. What are the forces on it? There is mg, there is the normal force. So there is the normal force. And remember, normal forces do not do work because they are at 90 degrees. There is mg, and there is the force of friction this way. Force of kinetic friction. And the motion is along this direction. So there is a 180-degree angle. And the length is the 6 meters. So force of friction times the distance moved times d, which is the length of the plank here, of the incline, times the cosine of 180 degrees. Okay, and I will just keep everything in symbols until the end. Or actually, I could simplify something here. mgy1, at the beginning, what was the height? Well, it was 0. It was at the bottom of the ramp, so it did not have, if my reference point for the gravitational potential energy is the bottom of the ramp is here, then it didn't have any potential energy here, gravitational potential. So this part is 0. Okay. So let's write this one again, one more time, and then we will write it even one more time. So I have 1/2 mv2 squared plus mgy2 minus 1/2 mv1 squared. This one was 0. Now what's the force of friction? It's the coefficient of friction times the normal force. And the normal force, if you remember, is mg cosine theta. So it would be mu k times the normal force, and the normal force is mg cosine of this 15-degree angle times the distance moved, d, times the cosine of 180, but cosine of 180 is -1, so this will simply be -1. Another good thing that happens is, now everything contains mass, so the mass can be eliminated from all parts. So let's see what we have now. Let's multiply everything by 2 to get rid of this 1/2 here and 1/2. So let's multiply everything by 2. When you multiply by 2 here, you get v2 squared. You get v2 squared. And then what? You multiply by 2, you get 2gy2. So plus 2gy2. You multiply by 2 here, the 1/2 goes away, and you have minus v1 squared. That's it on that side. And then you multiply by 2 here, you get negative 2 g d cosine of 15 degrees. I want v1. So I'll move v1 to this side, it becomes positive, and move this to this side, it becomes positive also. And so I would have, on the right-hand side, I would have v1 squared. On the left side, I have, oh, this should say v2. I would have v2 squared plus 2gy2. Move this to the other side, you get plus 2g d cosine of 15 degrees. And so v1 will equal to the square root of lots of stuff. v2 squared, v2 is 2.5, so it's 2.5. Let me write with this. Be 2.5 to the power of 2 plus 2gy2, so that's 2. G is 9.8. y2. y2 is 6 times the sine of 15. So 6 times the sine of 15 degrees plus 2g 2 times 9.8 times d, that's 6 also, times the cosine of 15 degrees. Cosine of 15 degrees. And, well, we'll just get a number, and it would be larger than 2.5. So you have 2.5 to the power 2, and then plus 2 times 9.8 times 6 times the sine of 15, and then plus 2 times 9.8 times 6 times the cosine of 15. Okay, and then you have to take the square root of what I got. I think that 12.26, 12.3 approximately. So I get V1 is 12.3 meters per second. And so the result is not the important part, it's the process of doing this. And let me just make sure that I have the number correct. So apparently I made a mistake. It should not be 12.3, it should be 6.3. And here is the reason, it should be 6.3. I don't know if you caught it or not. It should be mu k. I forgot the mu k. I forgot the mu k here. So it should be 2 mu k. And then here you have a mu k which is 0.025. So that will make this number smaller when you multiply by 0.025. So overall, this one will not be 12. It would be 6 something. Sorry about that. All right. So here's what we did. Our system was the mass plus Earth. So there is kinetic energy in the mass, and then the potential energy associated with the interaction of the mass and Earth. The external forces are the force of friction and the normal force. The force of friction, the normal force does not do any work because it's perpendicular to the motion of the object. The force of friction does work, and it does negative work. And so what we did, we said the energy at the beginning, at the end, minus the energy at the beginning, should equal to the work done by this non-conservative force, the force of friction. Sure, you could add the work done by the normal force, but that's 0. It just goes away. Let's continue. Okay, the next thing I want to discuss, the next potential energy that's fairly common is the potential energy of due to the interaction between a mass and a spring. So here is how it looks like. If you have a mass on a spring, it will look like this. It could be vertical, it could be horizontal. We first oriented horizontally so that the motion is horizontal, and we don't have to worry about vertical motion and the interaction with the gravitational force. And so here's the spring, and it's on its natural position here. And if you take a mass and you attach to the spring and you stretch the spring a little bit, so now the spring is attached to a mass, and it is stretched by a distance x. And remember, we said the force of the spring will be, if x is positive, if x is to the right, the force will be to the left. And if x is to the left, if you compress the spring, the force will be to the right. And we said that that force was equal to negative k times x. So when you plug plus for x, k should be negative to the other way. And we plug negative for x, k will be positive, meaning to the right. And we said we could associate a potential energy with this that is 1/2 k x squared, so that the force will be negative du dx, and that is equal to negative kx. Negative kx. When you take the derivative with respect to x, you get kx. Okay? Minus kx. Okay, so now our system will consist of the following. Our system will consist of a spring plus the mass, So the force of the spring on the mass and the force of the mass on the spring will be internal. And so we say the kinetic energy plus potential energy due to their interaction, the kinetic energy of the mass, because the mass is moving, the spring is massless. So we say the mechanical energy at the end should equal to the mechanical energy at the beginning, because there are no external forces doing work on this system. So think about it. As the mass moves back and forth horizontally, gravity is external, but gravity is not doing any work. If you move to the right and left, gravity is perpendicular, so it does not do any work because it's at 90 degrees. There is normal force if the mass is sliding on this frictionless surface. So there is normal force, but the normal force is perpendicular to the motion, and so it's not doing any work. Another external force is the force of the wall on the spring, because the spring is attached to the wall. That's a non-zero force, but it's not doing any work. Why not? Think about it. Why isn't the wall is attached to the spring? Why isn't it doing any work? Well, look at this point of attachment. Remember, to do work, you need to apply a force over a certain distance at an angle that is not 90 degrees. If the angle is 90 degrees, your work is zero. If the force is zero, the work is zero. But if also the displacement is zero, the work is zero. But this does not displace. The wall is rigid, the wall doesn't move front and back. It's fixed, so it's not doing any work. Okay? So the wall does not do any work. So we conclude that the external work is zero, and therefore the energy at the beginning should equal to the energy at the end, and our force here is conservative. So how does it look like? It will look like this. 1/2 mv2 squared plus 1/2 kx2 squared is equal to 1/2 mv2 squared v1 squared plus 1/2 kx1 squared. Right? This is the kinetic energy at the end, and this is the potential energy at the end. This is the kinetic energy at the beginning, and this is the potential energy at the beginning. All right? Okay, let us consider an example here. So we have a spring that's in a lab. So let me draw it and write it down. Actually, I notice it's 28 minutes already and my video will shut down. So let's do this in the next video segment. Let's do it in the next segment.